Christine Berkesch grew up in Indiana and received her BA with honors in mathematics from Butler University in 2004. And then she attended the EDGE program. I just found out from a talk I just went to by Dawn Lott that Dawn was her algebra teacher in that program. And you can see the result of EDGE. Let's keep it going, EDGE. We need more people like Christine. Anyway, after the EDGE program, she attended Purdue University to get her PhD in commutative algebra under the supervision of Uli Walter, who has Minnesota connection, and he was a student of Gennady. And as it happens, Uli is married to Mimi Botin, who was one of my husband's students. My husband's name is Peter Olver. So she received her PhD in 2010, and then went to Duke University as an assistant research professor and worked with Ezra Miller, who also has Minnesota connection. They stole him. And then after that, she worked at MSRI for the fall semester of 2012 in commutative algebra with her mentor, David Eisenbud. He has no Minnesota connection, just MSRI. Berkesch moved to University of Minnesota in 2013 and is currently associate professor, hopefully soon full professor. She is an editor of La Mathematica and the Journal of Software for Algebra and Geometry. Please check La Mathematica outside. There is a big poster out there. Berkesch is committed to increasing equity and diversity in mathematical sciences, working with AWM, of course, the EDGE program, of course, Math Alliance, and the organization of workshops, including a graduate program in commutative algebra for women and other mathematicians of a minority gender in 2019, and Roots of Unity workshop, which just ended. And she's going to be talking about the geometry of toric syzygies. Syzygies is one of my favorite words. It's a hard word to say, but I love it.
Thank you so much, Cheri, and thank you to all of the organizers for having me speak. It's really an honor and a pleasure to be here, especially since we get to be in person. It was worth the 2-year wait, for sure. So I want to just go ahead and dive in and tell you a story. This is going to be a story in 2 parts. So the first part is going to be a classical story about a regular old projective space. And then the second part will be a generalization, a generalized setting, where we try to transfer some of the results from the classical setting. So let's start. Before we get to the word syzygies, let's do some, the first thing you need to do any algebraic geometry is that you need to understand the algebra geometry correspondence. So on one side, we have ideals in a polynomial ring. We'll say in m variables, and then on the other side are varieties, and these are just 0 sets of polynomials. So collections of points that simultaneously zero out some set of polynomial functions. And so for instance, we have our parabola here given by x2 being equal to x1 squared. So that's an example of a variety. And what do we want to look at today? Well, there's a problem here. And the problem is that if I hand you a collection of FIs, some polynomials I want to look at the geometry for, their degrees alone don't tell you that much about the geometry of their variety. So it turns out, though, that we don't have to add too much more to get some very powerful geometric information. And so the solution comes in this word syzygies. Okay, so before we go on, we really need to talk about what that word means. All right, so a syzygy is a very fun word to write in cursive, but also it has a very careful mathematical meaning, and it's just the relation between columns of a matrix. So you can see here, I have this matrix phi with 3 columns, and then you'll notice the first column, if I multiply it by y squared, subtract off xy times the middle column, that zeroes out the first row. And then if I add in x squared times the third column, that zeroes out the second row, and I just get the 0 vector. Okay, so that is a syzygy. The thing we're calling a syzygy then would be a column vector consisting of these 3 coefficients. Okay. And historically, the word syzygy comes from astronomy. It's a word to describe celestial bodies coming together in line, at least 3 in a line. You should think of an eclipse. Right? So these planets, stars, other celestial bodies come into line, and they're said to be in syzygy, just like we lined up here our 3 columns. We lined them up using those coefficients to zero them out. All right, so I told you that syzygies encode geometry, and so in order to do that, we want to iterate taking syzygies and take as many as we can. So when we put a lot of syzygies together, that's called a minimal free resolution. So in terms of the homological algebra, this is an acyclic free complex, and we don't want to do anything more than we have to. So we're not going to use units in the entries of our matrix because those would be automatically related to other columns in the matrix. Okay. So here's an example. It's hard to be an algebraic geometry talk without a twisted cubic, so here you go. So this is a picture of the twisted cubic. Here are 3 equations that we could use to cut out our twisted cubic. And so I can think about the ideal generated by these 3 polynomials, and that's what I'm calling I of y. And if I want to make a complex with homology only in the 0th spot, so that here I'm getting S mod I of y, I just need to line up my generators for the ideal in this row matrix, row vector. And then I want to start looking at relations between those. So I write things from right to left so that I can multiply matrices. So here I can take this row now and multiply it in a dot product fashion with that column. And you'll notice, if you want to check quickly, x0 times this plus x1 times this plus x2 times this gives me 0. And then similarly over here. So a couple other things. So you'll notice here I have 3 entries, so that I have a 3 right here to keep track of the 3 columns. And then this 2, the sign is just a convention, but the 2 here is telling me that the polynomials here that you see are all degree 2. And then going on here, I have 2 columns, so this 2 is telling me the number of columns, and this 3 is bumped 1 from the 2 to tell you that the entries in this matrix are degree 1. Great. So now going back to the algebra geometry correspondence, we get a tighter relationship when we allow ourselves to consider ideals together with their syzygies compared with their 0 sets or their varieties. And once you have the syzygies in hand, you can get a hold of all kinds of really wonderful geometric information. So here is a short list. There are many more things, but in fact, there's a whole book just about this subject called The Geometry of Syzygies by David Eisenbud. And so I've listed here some of the things that this book covers, and I'll try to hint at least the first few on this list today. Okay, so to dive into that story, let's look at our polynomial ring and think about homogeneous polynomials. So if I restrict myself to S sub d, that'll be my homogeneous polynomials of degree d. And if I take the direct sum in all degrees, then I obtain this nice graded decomposition of the whole polynomial ring. And all the better, each of these pieces then is actually a finite dimensional vector space over my ground field, which I've chosen to be the complex numbers here. And we know how to count this, right? The total is m plus d choose d. A quick reminder of this calculation. So if m is 3 and d is 5, here's an example of a monomial of degree 5 in 4 variables, excuse me. And so then I can take my 3 zeros, line them up, and then 2 2s. I'm going to add the sequence 1, 2, 3, 4, 5 to this so that I get a strictly increasing sequence. And then that is going to be some subset of m plus d. So in order to get all monomials, I need to take 1 through m plus d and choose d elements. Okay. So this goes back to David Hilbert in the late 1800s. And I just wanted to look at this value in the quotient now. Once we quotient by our ideal, we're going to keep the same ideal. So this is the ideal for the twisted cubic. If we look in degree 1 or in degree 0, we just have the constants. So we have a one-dimensional vector space. In degree 1, we have the span of our 4 variables, so that's dimension 4. When we get to degree 2, something interesting happens because now I have these 3 binomials. So these monomials are still linearly independent from the rest, but now these 2 monomials span the same linear subspace of this vector space of degree 2 polynomials, and so forth. So in fact, instead of getting 10 monomials, I have 3 relations, so now that this is a 7-dimensional vector space. If you go on to the next, to degree 3, it turns out that there are 10, and so forth. And it turns out, actually, that when d is at least 1, the dimension of the dth homogeneous part of this quotient ring is 3 times d plus 1. So it's polynomial in d. And so this right-hand column is computing something we call the Hilbert function. And this value here turns out to be something we call the Hilbert polynomial. So from Hilbert's work, we see that given any ideal in this polynomial ring, if we look at its Hilbert function, which is this side over here, it is eventually equal to some polynomial evaluated at that degree d. Okay, and so we just saw for the twisted cubic that this was 3 times z plus 1 here, where I can put d in, and if d is 1 or higher, then we win. We can use this polynomial to find the function. It turns out there's some really nice things encoded in this polynomial. So for instance, if I just take any curve in a projective space, its Hilbert polynomial has leading coefficient, degree of the curve, and constant coefficient, 1 minus the genus. So in particular, this Hilbert polynomial is encoding everything we need to get a topological classification for this curve. I consider that a really beautiful, powerful story for this polynomial, and we're only in the linear setting still. But there's more. So for any variety inside of a projective space, you can in fact see the degree and the dimension from this leading term. And there is more to this story as well, but for the sake of time, we're going to have to keep going. So I told you this was to talk about syzygies, and now I've kind of changed gears, but it turns out that this is where syzygies come back. Yeah, so Hilbert wanted to prove this theorem, and in order to do it, he needed the syzygies. Okay, so this is why. So here is my minimal free resolution for the twisted cubic that we've already seen. And it turns out that these bookkeeping devices are giving me degree 0 maps throughout this complex. So in particular, if I fix a certain degree, I now have a complex of vector spaces. And so if I want to compute the dimension of the homology here, I can look at the dimension in that fixed degree in terms of alternating sums. And so here, that's what I've done. I've looked at this SD, and then 3 times this thing, and then the 2 times this S minus 3 in degree D. And if you untangle what the notation means, you come out with 3D plus 1. All right, so this is great. If you can make one of these complexes for any quotient ring like this, or even a module, then you get, using this formula at the bottom here, you get a polynomial here, as long as you know that the things that you're adding up here is a finite alternating sum. So that's what Hilbert showed. Right, so in the same paper, in order to get at the Hilbert polynomial, Hilbert proved what we call his syzygy theorem. And here what we're seeing is that there's not only is this minimal free resolution going to be finite in length, but it's actually going to be bounded in length by the dimension of the ambient projective space. Okay, so that's a very nice tight bound. And here then right away, hopefully you're seeing, oh, that's already a geometric property in the homological algebra, right? Because now I have this complex that has at most m maps in it, and I was working with objects inside of this m-dimensional projective space. All right, so I want to tell you a few other places, maybe a little bit closer to us from history, where syzygies show up to give us some geometry. So here I have this invariant I'm going to call the regularity, and it is essentially telling me how high the degrees of the polynomials are in the entries of the matrices that make my free resolution. Okay. So there's some issues with the homological degree and keeping track of that, but for the sake of this talk, the maximal degree of a syzygy works great. And so in particular, in our example for the twisted cubic, we saw polynomials of degree 2 and polynomials of degree 1, and so here the regularity is 2 for this example. And this invariant goes back to David Mumford in the 60s, and what he did was take this invariant for regularity and use it to link bounds on degrees of syzygies with bounds on vanishing for sheaf cohomology. And sheaf cohomology is encoding a lot of subtle and geometric information. So now we have this really nice invariant that's connecting these two ideas. Okay, and then next is this Eisenbud-Godot theorem. So now we're in the 80s, and they gave a few equivalent ways of thinking about regularity in terms of a free resolution for something, or syzygies. So here you can see, so saying P regular means that P is something that is at the regularity or higher. So saying we have this is something related to the regularity, and then we're going to truncate our quotient ring in that degree and only look at the pieces of that quotiented polynomial ring in that degree or higher. And it turns out that then that truncation should have regularity 1, which means, kind of based on what we saw in the last slide, that we really have a linear minimal free resolution for this piece of the module, or of this quotient ring. So right, we know that once we go up high enough into our module, we can chop off the lower part and then be given just a family, a series of matrices involving only linear forms that tell us about this quotient ring. Okay. All right, so one more. This is due to Mark Green from the late 90s. And here, I'm not going to tell you the full theorem because I think it's too technical for this talk. But I will say that he gives a very nice explicit bound on the linear strand of syzygies for one of these quotient rings. And here, when I say linear strand, there may be higher degree terms or higher degree polynomials in the matrices, but we could restrict to the part of the minimal free resolution where there are only linear forms. And then looking at sort of how far back do we go and have linear forms in the free resolution consecutively. And in his formula, which I haven't given you, but you'll have to trust me, that in this formula, there are some very subtle geometric invariants hanging around that are detecting the length of this linear strand. So not even the whole minimal free resolution resolution itself, but just little pieces of it alone already have a lot of interesting geometry. Okay, so to summarize these first few bits here, we have these 4 classical results. So first was Hilbert's syzygy theorem telling us that the dimension of our ambient space, our projective space M, was bounding the length of our minimal free resolutions. Then we had Mumford's connection between syzygies and vanishing on sheaf cohomology. Then Eisenbud-Godot telling us that regularity tells us about these linear free resolutions. And then finally, these subtle geometric invariants that show up in Green's theorem. So now I want to switch gears and take this setting and abstract it. So to do that, first I want to go back to the projective space and think about how we build projective space, or at least one way that we can build projective space. The way I want to do it today is to start with a polynomial ring, now in m+1 variables, and that should correspond to an m+1 dimensional affine or Euclidean space. Let's see. So this m, right, these m+1 variables give me coordinates for this c to the m+1. And then I want to think about my projective space as identifying lines through the origin with points. But in order to do that, I need to remove the origin. Well, the origin is the 0 set for all of the variables being equal to 0. So if I remove the variety of this ideal here, this is the origin. And now I can ask for just a single C star variable to scale things. And of course, how do I get a line through the origin? I take a vector and I multiply all the coordinates by a constant. So this vector of all ones is meant to tell me how this C star is acting on this space. And when I quotient, then my orbits turn into single points. And so now I've made my projective space P to the M using my lines through the origin in a Euclidean space of 1 dimension higher. Okay? So now we want to do this, but in a more general setting. So to do that, all right, we have a polynomial ring in now capital N variables, and that's going to be our C to the capital N. And I want to remove some locus of points that's going to correspond to some nice ideal in this polynomial ring. And then I'll also have a matrix that now is going to be R by N, because I now have a C star to the R acting, so some other torus action. And then I'm going to quotient by that torus action. So just like for projective space, we had a big Euclidean space of 1 dimension higher. We removed the origin and modded out by scaling everything. Now we have a more general setup of that. All right, so that's what we'll call a toric variety. And for the purposes of this talk, I really want my toric varieties to be smooth and projective. Yes, that's the setting we'll work in for today. And I have 2 examples for you here. These are 2 different 2-dimensional toric varieties that are pictured for you combinatorially. So for both of these examples, we're using a polynomial ring in 4 variables, 2 I called X and 2 I called Y, because this ideal B I want to look at is taking the X's and intersecting with the ideal generated by the Y's, so that all the generators here look like Xi times some Yj. Okay, so this first picture is keeping track of a P1 cross P1. So here my scaling is happening in the first 2 coordinates of the P1, the X coordinates, with the first component of my torus. I have a C star 2 here. And then for the second P1 here, I have scaling in the second 2 coordinates. And so then these X's correspond to the origin needed in a 2-dimensional space to get that P1, and these Y's for this one. Okay, and so the way you can think about this here is that like my C star squared is this origin, and then I fill in coordinate lines, and then finally an origin. And if you paste these pictures together, you get a compact variety. And then this is a Hirzebruch surface. This is this other one where now I've taken this line here on my P1 cross P1 and I've slanted it up. Okay, so now I have a P1 bundle over P1 right here. And so in all of these situations, we can take this initial setup data and make some combinatorial pictures like this, these polyhedral fans that are very useful in keeping track of the geometry of these toric varieties because they really show us the orbit structure fully. Okay. All right, so now going back to the questions I asked at the beginning, or the theorems I showed you at the beginning, we have these questions now for this more general setting, right? So we can ask if there's still a way to bound the length of a minimal free resolution or some other set of syzygies. We can ask about this regularity, that what is, is there an analog in this multi-graded setting? And also this idea of linearity, right? Linearity made sense when our grading group was the integers, right? But once you have, you're using vectors with length more than 1 to give you degrees on your polynomials, what does linear even mean? And then last, of course, the whole hope out of all of this would be to do things like Green's theorem, where you can get some really beautiful geometry out of this homological algebra. All right. So here's the challenge. There's a catch, right? There's always a catch when you move to a more general setting. And the catch is that when you move to something that isn't a projective space, then this ideal B, this ideal that you used to remove something before you quotiented from your torus action, this is now strictly living inside of the ideal generated by all the variables. Right? So for projective space, these two are equal. And that means that when you're asking for minimal free resolution, so avoiding units, and looking at this ideal, they're kind of doing the same thing. But now, geometrically, B is telling you info about a lot more points up in that big Euclidean space that you started with. And that creates some problems. So using minimal free resolutions in general, like we know them over the polynomial ring, is not great. So maybe before I say more about that, just say that David Cox has a beautiful paper from '95 that gives a version of the algebra geometry correspondence in this toric setting. And so we still have some homological algebra, it turns out, on both sides. So over here, we still have this polynomial ring in lots of variables. And now we can look at minimal free resolutions, but they're typically going to be much longer than the dimension of the ambient space. So that's the downside. On the other side, we could also ask for homological objects in terms of the sheaf theory, and locally free resolutions, Grothendieck showed us, were short, meaning bounded by the dimension of the ambient space. The problem with these are that they come from vector bundle resolutions, and vector bundles are not the easiest to write down sometimes, often, right? So over here we have nicer, more simple descriptions, but way too long. And here things are short and compact, but we don't really understand the terms. Okay, so now we're kind of stuck in limbo between these, not knowing what to do because neither one is really what we want to work with. So what should we do? And the answer is try to split the difference and find something in the middle. Okay. So let's look at this example. Here I have a hyperelliptic curve of genus 4 inside of P1 cross P2. I'm not going to show you all the generators. There are, 8 generators here of various multi-degrees. So you'll have to trust me. I can show them to you later if you really want to know. But you can see our P1 cross P2. I have my P1 variables in the X and the P2 variables in the Y. And as a Riemann surface, my curve looks like this. And so the minimal free resolution now, this is a 3-dimensional space, so 1, 2, 3. I would hope to stop here and have a 0 here if I wanted a Hilbert-Syzygy type theorem to be in play here. But of course, this goes on longer. Okay, okay, so this is where my co-authors and I joined this story. So we have our same toric variety. I just put this back up here to remind you the notation. And what we want to do now is keep the nice homological algebra over the polynomial ring. So that's our S. But instead, we want to allow ourselves just a little bit of homology. Right? And the homology that we're going to have is homology that is all supported in this irrelevant ideal B. so that when we pass to the geometry, it disappears. Right? Any of that homology is no longer relevant to the geometry in play. So there are different ways of saying this. One way is to say that our complex sheafifies to an acyclic complex. Another way is to say that this homology is B-torsion. All right, so at least in this example, you've seen one virtual resolution, and that's this orange complex right here. So it's a subcomplex of this minimal free resolution, and you'll notice it actually gets us shorter by one extra than we needed for a Hilbert syzygy bound. And so this is an example of one virtual resolution for this curve. But there are many, many more. All right. So here is a Hilbert syzygy theorem we were able to get in this virtual setting when our toric variety is a product of projective spaces. So here, now we can show that there is always some virtual resolution for any module in this setting that has length at most the dimension of this ambient product of projective spaces. Okay, and it turns out there are a couple other settings where this holds. So here's a Brooks surfaces, using the work from these three authors, adapts our proof very quickly to cover Hirzebruch surfaces as well. And then my postdoc, Jay Yang, showed that on any smooth, complete toric variety, monomial ideals always have short virtual resolutions. All right, so that's the Hilbert syzygy theorem, but we had a few more theorems to go through. So next, before I do that, I had a quick aside. So this is some work from my RU students, and then also a group of a student and two postdocs. So we were looking at trying to do even better at bounding the length of these complexes. And in general, these complexes are bounded in length below by codimension. And so the shortest they could be is codimension. And so this is two instances where in a square-free monomial case, we were able to show a nice family of monomial ideals that have this shortest possible length for a virtual resolution. And this is a picture, in the second paper, this is a picture that we used in our combinatorial construction to make this happen. All right, so now multi-graded regularity. So we had single variable regularity for a projective space, going back to David Mumford. And in 2005, Diane McLagan and Greg Smith introduced this notion of multi-graded regularity for a toric variety based on some geometric properties. Now, they aren't the only ones to put out a version of multi-graded regularity, but we felt in our setting that this was the one that mirrored most closely what we were hoping to do with bounds on cohomological vanishing. And of course, now our grading group is always going to be z to the r, right? The dimension where r is the dimension of the torus that's acting to create our variety. And so instead of giving us an integer, now we need some set of vectors inside of z to the r. And it turns out that these regularity regions always form these kind of staircasey diagrams. So they're closed under addition by natural number vectors in this case. And so you get sets of points that look like this. And so for the curve you saw previously, this is the regularity for S mod I of C. All right, so the good news is that, like I already said, this definition is great because it really matches up with those bounds for cohomological vanishing that are telling you a lot of geometry. The bad news is when you go and look at the minimal free resolutions and try to link that up with the geometry, the way we saw in Mumford's work, as well as the Eisenberg-Godot theorem, that's just not there. It's very hard to tell what the regularity is based on what gradings or degrees of polynomials you see in a minimal free resolution. So then we were hoping that these virtual resolutions might do a better job of capturing this set that's telling us important geometry. Okay, so we just need a little bit of notation here. So I always have my irrelevant ideal B, that is some monomial ideal, and I can look at its minimal free resolution over the polynomial ring. And that will have certain degrees of polynomials in that, right? So it's a fixed thing. And so for P1 cross P2, degree 0 is just 0, 0. Degree 1, all of the forms are xi times yj's. So they're 1, 1, degree 1, 1. And then for in homological degree 2, we have 2 different places, and then 3, and then at the end, there's just a single degree again. But for any given toric variety, we'll just get, one collection of these delta i's. And what we were able to show for our products of projective spaces is that this S mod I of y is D-regular, so meaning D belongs to the regularity region, if and only if, when we shift our quotient ring around, we get a virtual resolution where the degrees along the way are bounded by these delta i's plus natural number vectors. Okay, so this is one way to think about capturing the regularity in terms of all of the virtual resolutions a module has, or a quotient ring has. So I can look at all of the virtual resolutions, and that in some sense sees the multigraded regularity, which, at the time we first discovered this, we didn't actually have an algorithm to compute the multigraded regularity. So this was very, very exciting to us at first. Fortunately, now we can also compute the multigraded regularity in Macaulay 2 even. It is implemented. It's wonderful. All right, so a theorem, here's another theorem that's using multigraded regularity connected to certain virtual resolutions. So in this setting, I want to look at some subvariety of my product of projective spaces, and then I want to pick D so that it's in the regularity. And then I'm going to look at my minimal free resolution, and I'm going to throw away a bunch of terms. And those terms are going to come from things that are not bounded above by this D plus N. Right, so N is the dimension of each component of my projective spaces, and D was my regularity vector. And it turns out here, if I use the vector 4, 1, which is in the regularity, then the orange complex is what survives, and the rest of this goes away to make a virtual resolution. Okay, and so, if we go back. So the regularity here, we just use this 4, 1, but you could get 2 other nice virtual resolutions from this minimal free resolution just using these 2 other corners here. Okay, so I don't want to say a ton about the rest of this. I will just say that we show a lot of things in this paper that we are really excited about in terms of taking our now virtual syzygies and turning them into interesting toric geometry. In particular, so this embedded deformation theory, right, we could use the Payne of Schlesinger comparison theorem again in this toric setting as opposed to its original projective space setting, and show that very similar claims for now virtual resolutions of pairs from the previous slide will tell us about the embedded deformation theory for our subvariety Y. So I feel that that's good evidence that virtual resolutions are encoding some really, excuse me, subtle and beautiful geometry. And then you can see here we have a few other things as well. Okay, so this kind of we've taken care of the Hilbert syzygy theorem. We've also taken care of now understanding how regularity can be encoded in syzygies as it relates to vanishing of sheaf cohomology. So now we want to move on to linear syzygies. Okay, so this is a pretty recent paper by one of my graduate students, Mahrad Sairafi, and then Juliette Bruce, the postdoc in Berkeley, and Lauren Cranton-Heller is also a grad student in Berkeley. And so what they were able to show now is a characterization of regularity in terms of truncations having quasi-linear resolutions. So what you should think here is this Eisenberg-Godot theorem was over a single projective space, and here then you just had to erase the word quasi. So the meat of this theorem is really in what does quasi-linear mean? Okay, and so what quasi-linear means is a very specific set of vectors where you're allowed to have degrees of your polynomials in the matrices as you go along in your virtual resolution. Here it's actually a minimal free resolution. So 0, you have to live in here. So this is for P1 cross P2. And then as you move 1, now you're allowed to move a little bit bigger. And then it kind of starts getting more stair-steppy the higher you get. Okay. All right, so this notion of quasi-linear is definitely giving us now a good multi-graded analog of the Eisenbud-Godot theorem for a single projective space. And then very recently, just a couple months ago on the archive, Michael Brown and Daniel Ehrman have a stab at this linear strand theorem of Mark Green's in the virtual setting. But there's actually still a lot more work to be done, kind of taking all of Green's work and moving it into this more general setting. So I really feel like this is just the beginning for this part of the story. All right, and I wanted to make sure to, I think my favorite part about this topic and the work that I've been doing in this area is that a lot of people have come alongside doing it with me and writing some really beautiful papers. And there's been a lot of younger mathematicians, meaning more junior mathematicians working on this, as you might notice here from the photos. And I've really been pleased to have the pleasure of working with a lot of them and benefiting from their theorems. And I really do think this is still just the beginning, that there are so many open problems to understand about virtual resolutions and lots of beautiful geometry to find in those syzygies. So I think I'll stop there. Thank you.
Any questions?
So you define, you talk about virtual colonies. My understanding is the resolution may not be the same length for the first idea.
You're saying like different virtual resolutions?
Yeah.
Yes, yeah, absolutely. Different virtual resolutions can
So
definitely have different lengths.
My question is the geometry aspect of virtual colonies.
Yeah, that's a great question. And I think we don't quite know exactly yet. I mean, there's essentially, when you think about like being equidimensional and unmixed, like those things are still gonna hold in up to saturation by the irrelevant ideal. So that's one thing that's being detected. So in terms of the geometry, you're going to geometrically see components that look like a Cohen-Macaulay variety. But you've just, you have this piece up in the big affine space before you quotient to make your toric variety that is allowed to look really wild. And so that's what we really want to do with this virtual Cohen-Macaulay property, is kind of only worry about the things that are geometrically relevant.
I was just wondering if these would be reasonable questions to ask in other settings like Grassmannians or something like that.
Yeah, any Mori dream space, we could go ask these questions, certainly. But since we barely understand products of projective spaces, we're still working on that. I would be happy to do more things for here's a brick surfaces before we try and go wild.
Thank you. I had a very quick question. Calculating the syzygies is very difficult in higher dimension. How do you do those with?
I use Macaulay too most
Macaulay
of the time.
too, okay.
Yes, yeah. So there is a virtual resolutions package. That's this first paper here in the Journal for Software and Algebra and Geometry, and it's a really great package. It lets us do a lot of manipulations quickly with the complexes.
Thank you so much for a very interesting talk.
Thank you.